Okay guys, we have a quick video for you today. So the Snapmaker U1 is still not fully released yet. It's coming soon, I promise. It's very popular. Snapmaker are working hard to get it ready for us and consequently you. But we did a video about it a little while back and we focused on two things. So multicolor use and multi-material use. Tool changers have great advantage with multicolor, way less wasted filament purge and very quick prints compared to an AMS type device. It's great, but I am more interested in multi-material. Unfortunately, most people out there have only focused on two aspects of multi-material. One is supports. You can use dissimilar material as support, such as PETG and PLA as support, or vice versa. They stick just enough to be used as support, but only just enough to be snapped off very easily. Very useful tool, and you can find Thomas Sandlatter's video about it right here. The other one is compliance, which is also very useful. This is where you add a flexible part to a rigid part and make it suitable for bending and to resist fatigue over a greater extent of time. This is a great example. This is a compliant pliers where the pivot is a TPU grid instead of a rigid bearing. I love both applications, but we're just scratching the surface of what multi-material really means. So today, instead of layering dissimilar materials on top of each other on the Z for support or for using flexible parts simply for compliance, we're going to use dissimilar materials on the XY plane and using TPU not for simple flexibility, but for its other inherent quality, elasticity. First, we need to consider how strong dissimilar materials are exactly on the XY plane. Tom's video concluded with a little table on which filaments bond best and worst with each other. Now, this gives us a clue, but as mentioned, this was on the Z, and Z strength is always way weaker than XY strength. So, I mean, we have a clue, but we still need to test this. This is a sample of TPU mixed with a PETG, and we're going to put this in our Tensile tester and see what happens. This is our Tensile tester and it's based on Robert Cowan's design. However, I've changed a few things to use more metal parts, so it's somewhat more accurate. So what can we do with this strength? Well, I mean, there are functional applications that exist, but I kind of want to do something fun. In the past, we have designed and built these compliant rigid filament spring blasters, which are super fun, but not that powerful. They're just not strong because they're using a rigid filament as the spring, and for some applications that works, but there's just not that much energy stored in them. I want to change that by using a TPU and making a slingshot. Yes, slingshots are fun. Everyone's printed a slingshot. No, you haven't. At best, you've printed a handle and then got like a rubber band or a balloon or an actual slingshot band and attached it to it. No, very few people have actually 3D printed a slingshot. This is a print-in-place slingshot. You can actually really only do this with a tool changer or maybe a Cobra X, maybe, I'm not sure. The reason is this is a soft TPU. It's 30D actually, which is pretty much impossible to print on an AMS type device. So we know how much pressure we can put on this TPU. A little slingshot should be just fine to use, right? Let's find out. Hello. I'm scared too because there was a fine line with designing these bands. If it's too thin, it snaps. It snaps. It's not even the interface that's a problem. It's just weak. And if it's too thick, well, it's too thick. It's just hard to pull back. So there's a fine line. If it's too thin, then it breaks, but you need it to be thin to get that elongation. That's where the power comes from. But if it's too thick, then you actually can't draw it back, and yes, you need that elongation. Also, if it is too strong, then the amount of energy that you put into it by pulling back, it's not released in a 1-to-1 ratio. There is losses, and the thicker it is, the more those losses are. And when we were scaling this up to design a big one, that became pretty obvious. With just a tad more depth and width on the band, we did get more reliable bands, and on testing with a chronograph with a 20mm ASA ball projectile, we got some good speeds. And yeah, this totally destroys our records with the rigid spring blaster. This is way better. Okay, but what about something that is not ASA? What about something heftier? Look what just came in the post. Ooh. What do we got? This is the point where I probably don't have to tell you that something like this can be a tiny bit dangerous. Like, just use common sense, guys. Okay, let me just do the math. So half the mass, which is 32.76 grams, by velocity squared, which is 29.6 grams. 14 joules. Right? This is when I fully realized that me making a toy was actually me making something that could potentially hurt you a lot. In fact, slingshots have sort of occupied a legal gray area in a lot of countries, and if you have a design with something like an aimer or a wrist brace, then you might have issues in the following countries.
The Republic of Singapore, the Federal Republic of Germany, the Republic of Korea, the People's Republic of China, Canada, the Kingdom of Denmark, the Kingdom of Saudi Arabia, the Kingdom of United, and the American States of United America.
So let's go back to plastic projectiles. Yeah, lovely, semi-safe, high-speed plastic things. Yeah. So even these have super high energy compared to our rigid spring blaster. That's pretty high in comparison. So yes, you can fully 3D print a print-in-place slingshot that is actually very, very effective. And you can do this if you have a Snapmaker U1, another tool changer like a Stealth Changer or a Mad Max, or technically even a dual extruder printer, because you only need 2 filaments for this. You just need to know a couple of things. So 1, for the handle, use a rigid filament, and it's best to use PETG because it sticks well to TPU, and make that interface as sprawling as possible so that beam interlocking works well. 2, use the stretchiest filament you can. Our stretchiest is Recreus 60A with an elongation at break of 950%, but that's actually quite hard to print, and I had not great results with the U1. Not because of the extruder gear, but actually because of the distance between the gear and the hot end. It just kept buckling. And we ended up using Fiberlogy's 30D with an elongation of 875%, and that worked nicely. 3, taper your band. So for us, it was better to be thicker closer to the interface, and it's almost 2 millimeters there, and 1 millimeter closer to the projectile. The width is also tapered. It's 12 millimeters here and 9 millimeters there. Thinner might get you more stretch and better power, but it's weaker and it could break. That was for 30D. For stretchier, you can go a bit thicker. 4, don't be a dick. Just don't. Don't shoot at animals, other people, annoying billboards, or even Lucas.
Despite being very satisfied with this little toy and somewhat uncomfortable with the slingshot's safety, I still wanted to test the limits of what something entirely 3D printed can do with both printed BBs and steel. The highest speed we were able to get was about 32 meters per second. Generally, they were in the high 20s, but this is with both plastic and steel. The bigger the bearing, the slower the speed, but its density doesn't affect it so much, so with a larger steel bearing, it was slower, but it packed quite the punch. In fact, with a 20mm printed BB, the energy was 2.24 joules, with a 20mm steel BB it was 14.67, and with a 25mm steel BB it was 24.6 joules. Like, even the plastic BB is outrageous enough. I just wanted to show you guys that beam interlocking was strong with dissimilar materials. In a fun way. That's all. Oh well. I might see you next time if a BB doesn't bounce off something and hit me in the head. Later, guys.